Hello, chemists. This is Ms. Placino, and you are watching lesson 4.5 on hybridization. Today we're going to talk about what orbital hybridization is and why it occurs. Some goals for today's lesson. Explain what orbital hybridization is and which orbitals hybridize. We'll also talk about what sigma and pi bonds are and identify them in a Lewis structure. These terms, sigma and pi, first came up in lesson 4.3 when we introduced covalent bonding. We're going to kind of expand upon them today. And the big takeaway from today's lesson is to be able to look at a Lewis structure and determine what type of hybridization the atoms must have undergone and their molecular geometry. Now, hybridization is an advanced topic for a first-year high school chemistry course, but I know you can do it. We'll get through it together. Just stick with me and know it's okay to be confused. Let's get started. All right, I first want to start by talking about sigma and pi bonds. Let's look at a really simple molecule, H2. We know hydrogen has one valence electron, one total electron for that matter, and that it's in the 1s orbital. When two hydrogen atoms bond together, those s orbitals will overlap with one another, and a pair of electrons will be shared. We observe the same type of orbital overlap when we take hydrogen and fluorine, and this will hold true anytime we've got a valence electron in a p orbital. The s and the p orbitals will overlap and they'll share a pair of electrons. We'll see a sigma bond. Sigma bonds are the result of direct orbital overlap. Sigma bonds are single bonds. It's a little bit different when we have double and triple bonds. So let's look at oxygen. We know that O2, another diatomic molecule, has a double bond. If I was just to quickly draw a Lewis structure, it would look like this. When a double bond is present, one of the bonds in that double bond is a sigma bond, or you see that same direct orbital overlap. The other is a pi bond. And in a pi bond, you kind of just have the p orbitals not really overlapping with one another, but in a way it's like they're almost just like aware of each other. They can see each other, and that's going to lead to the spin pairing, one up, one down, and we have what's called a pi bond. So the sigma bond will overlap those two p orbitals, and then these two p orbitals, the ones that are like pointed up on the y-axis, they don't technically overlap, they just kind of align. If we look at nitrogen, and we'll draw a quick Lewis structure. We know nitrogen has a triple bond. A triple bond consists of one sigma bond and two pi bonds. And it's the same idea. Sigma, we'll see orbital overlap. Pi, they're just kind of aligned together. So that's the difference between a sigma bond and a pi bond. Let's look at a couple practice problems. We're just counting sigma and pi bonds. So I'm over in the practice problems, and I want to look at practice problem number 3. And I just want to count sigma and pi bonds. So I know every single bond is a sigma, and anytime I have a multiple bond, whether it's a double or triple, one of them has to be a sigma. So if I just start here, and I'm just going to kind of cross them out as I count. 1, 2, 3, 4, 5, 6. Let's say there are 6 sigma bonds. I'll do my pi's in blue. 1, 2, 3 pi bonds. It's as simple as that. And you don't really have any way of kind of like determining which of those 3 is supposed to be the sigma, which is the pi. It just, it could be any way you want to label them. As long as you know that a triple bond consists of 1 sigma and 2 pi bonds, you're good to go. All right, let's get back to the notes. Before we get into orbital hybridization, I want to backtrack and just talk about atomic orbitals for a moment and look at why hybridization theory even exists. So let's look at carbon. The quantum mechanical electron configuration of carbon, hopefully you feel pretty comfortable with quantum mechanics by now. 1s2, 2s2, 2p2. 6 electrons, that's where they are. If we were to draw an orbital diagram for all of the electrons in carbon, all 6 of them, we'd of course need the 1s, the 2s, and then 3 2p orbitals. So something like this. And if we start filling them, spin up and spin down, there it is. And we've talked about how pairs of electrons tend not to get involved in bonding, and unpaired electrons tend to get involved in bonding. So just by looking at the orbital diagram for carbon, it might look like carbon would only form 2 bonds. That pair of 2s electrons, that's not going to get too involved in bonding. These p's would, because they're unpaired. So it looks like carbon would only form 2 bonds based on our atomic orbitals. We know this isn't true. We know carbon always forms 4 bonds. So scientists had to come up with a theory of why this occurs. And they came up with atomic orbitals when the atom goes to bond, kind of hybridizing into these hybrid orbitals to explain the bonding behavior. So I've got a quick video to show you, kind of just trying to help you visualize what it means to have orbitals hybridize.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The 3 p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce 2 hybrid orbitals called sp, pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces 3 equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes, which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all 3 p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
Again, I'm sure that video didn't really clear up what orbital hybridization is, but I hope you can take away from it kind of what's occurring in hybridization. We saw the s and the p orbitals kind of blending together to create new orbital shapes. So the idea is that these are the orbitals that exist when an atom goes to bond, not when it's just a lone atom all by itself. So we're going to focus specifically on hybridization involving the s and p orbitals, and let's start by trying to apply that to carbon. Okay, let's start off with orbital hybridization in CH4. So we've drawn the Lewis structure for methane before. Carbon has 4 hydrogen atoms bonded to it. Again, if we kind of talk about the energy levels and sublevels and fill our electrons, we know that it looks like this. There are 2 p electrons and there are 2 s electrons. The idea is with hybridization, in this case, we're going to take the s and all 3 of the p's, and we're going to blend them together to create 4 equivalent orbitals. We know we need 4 because there are 4 sigma bonds. Remember, sigma bonds are just single bonds. So we have to have 4 orbitals created. Those single bonds mean orbitals have to overlap. This is accomplished, again, by taking our 2s orbital and our 2p orbitals and blending them together. We call this hybridization sp3. If you look at like the little superscripts, technically, one's not written there, but we know it's there. I have 1 plus 3 equals 4. If I just add up the exponents, it tells me how many hybridized orbitals I'm going to form. So again, we call this sp3, and it's going to give us our tetrahedral geometry, as the central atom has no unshared pairs of electrons and 4 sigma bonds, or 4 atoms bonded to it. Other types of hybridization exist as well. All right, let's look at another type of orbital hybridization. Go ahead, try to draw a Lewis structure for CH2O, formaldehyde or methanol. Hopefully you've drawn something that looks like this, where you have carbon double bonded to an oxygen, and then you have each hydrogen single bonded. Now, if we think about carbon, the 2s and 2p atomic orbitals haven't changed at all, but we know they're going to hybridize in order to create enough bonds. How many sigma bonds do we have present here? Yeah, we've got 3. 1, 2, and then one of those in the double bond is a sigma bond. How many pi bonds? Just one. So if I've created 3 sigma bonds, I'm going to need to hybridize 3 orbitals together. And if I have a pi bond present, I know at least one of those p orbitals has to remain unhybridized. So 3 sigma bonds, 3 hybrid orbitals have to be created. Any thoughts on how many s's and p's I need to blend together to create these 3 hybrid orbitals? Yeah, hopefully you're thinking the s orbital and 2 of the p orbitals. We'll leave one of the p's unhybridized, so it will be able to participate in the pi bond. Now, if I have taken 1 s and 2 p's, take a guess at the type of hybridization that we call that. Yeah, this is sp2. 1 s orbital, 2 p's, sp2. And we get this trigonal planar geometry. That's going to allow us to form those 3 sigma bonds. We still have an electron in the p orbital to form the pi bond. Nicely done. All right, let's do one more type of hybridization. Let's look at carbon dioxide. Go ahead and draw a Lewis structure for that. In carbon dioxide, carbon is double bonded to both of the oxygen atoms. So again, its atomic orbitals stay the same. It's only when carbon goes to bond that hybridization is going to occur. In this case, how many sigma bonds do we have? We've got 2. So we're going to need to create 2 hybrid orbitals. How many pi bonds do you see? We've got 2 of those as well. So that means I have to leave 2 of the p orbitals unhybridized. So 2 hybrid orbitals created. How are we going to create them? What are we going to combine? The s will combine with the p. We'll leave those other 2 p orbitals alone. They'll be unhybridized so that they can participate in forming the pi bond. And if I've taken an s and a p orbital and I've hybridized them, what do we call the new hybrid orbitals that we produced? Good, those are SPs. And sp hybridization in carbon is going to give us a linear geometry. All right, I know this is confusing and you might feel a little bit overwhelmed. Don't panic. Before we move into practice problems and I kind of let you know what my expectations of you are as far as hybridization is concerned, I just want to bring a couple things to your attention. We focused on carbon, but atoms of other elements, in particular nitrogen and oxygen, also undergo the same type of hybridizations that we just played around with, sp2, sp3, and sp. As you get to larger atoms, such as phosphorus and sulfur, which we know can expand their octet, that really stems from orbital hybridization. So I just want you to be aware of the fact that you can have d orbitals that kind of get involved with hybridization as well. We can have all 3 of the p orbitals and d orbitals get involved. That's going to lead to a trigonal bipyramidal geometry, and we call that dsp3 hybridization. The same thing happens with sulfur. We can take 2 d orbitals, combine them with s, and 3 p orbitals to give us the octahedral geometry. It's the same idea where you're taking those orbitals and you're just kind of mixing them together and you're creating shapes that aren't really s's, p's, or d's on their own. But you end up with these hybrid orbitals that exist when we see atoms like phosphorus and sulfur, for example, bonding. Okay, let's get into some practice problems and try to make more sense of this. Hybridization is always confusing for new chemists. I'm not going to really hold you responsible for drawing these hybrid orbitals, definitely not their shape, but even taking like the orbital diagrams and showing how hybridization occurs. I think that's a little bit too much to deal with at this point in the game. What I do want you to be able to do is to look at a molecule. You can notice these are slightly larger than what we've been dealing with, and determine the hybridization at a certain atom and the geometry that that atom is going to exhibit. There is I don't know if I want to call it a shortcut, but I can't think of a better phrase for it, so we'll keep it shortcut. If you want to try to figure out the hybridization that has occurred, the best way to do that, or the easiest way to do that, is just to count the number of things that are attached to the atom of interest. By things, I'm talking about atoms and unshared pairs of electrons. So if there are 4 things attached, again, any combination of atoms and unshared pairs of electrons must be sp3 hybridization. 3 things attached, well, that has to be sp2 hybridization. Only 2 attached, that's sp. And we're going to treat single, double, and triple bonds as the same. It doesn't really matter how 2 atoms are bonded together. We're just interested in how many atoms are attached to the atom in question and how many unshared pairs of electrons are present, again, for the atom in question. So let's try it out. Let's see if we can apply it, and maybe that'll make a little bit more sense. So I'm going to go back to question number 3, the one that we started, and we're looking at atom 1. So nitrogen has been labeled atom 1 in this case. How many things are attached to nitrogen? And I know that's super vague, but again, things are unshared pairs of electrons and atoms. All right, I see 1 unshared pair of electrons, and I see 1 carbon atom. So that's 2 things that are attached, or bonded, or connected to, however you'd like to think of it. So if I've got 2 things attached, I must have sp geometry, hybridization, excuse me. It doesn't matter that nitrogen and carbon are connected by a triple bond. We have 1 atom, 1 unshared pair of electrons. That has to be sp hybridization. Nitrogen is only bonded to 1 other atom, so what sort of geometry will we see, or I guess technically, will nitrogen have? Yeah, that's going to be linear. Let's move over to carbon number 2, or atom number 2, which is carbon. No unshared pair of electrons, but again, 2 things bonded to it. That's sp hybridization as well. And again, we're going to see a linear geometry. Our third atom is this carbon atom. I see 1, 2, 3 atoms bonded to carbon, no unshared pairs of electrons, so 3 things. That must be sp2 geometry. Let's see, sp2 geometry. I've got 3 things bonded to the central atom, no unshared pairs of electrons. That's going to be a trig planar geometry. There we go. I know this video is running a little bit long, but I also know that this is a confusing one for new chemists. Try out number 2. Pause the video and try it out. We'll review it together. All right, just to wrap up, so I went ahead and I took care of the sigma and pi bonds. Hopefully that's pretty straightforward. You're just counting. Atom 1 is carbon. Carbon's got 4 things bonded to it. That has to be sp3. Since there are no unshared pairs of electrons, that's got to be the tetrahedral geometry. If we move over an atom to the right, we've got nitrogen. 2 atoms bonded to nitrogen, 1 unshared pair of electrons. That's 3 things, if you will, attached to nitrogen. So that's sp2. Unshared pair of electrons, 2 atoms bonded. That sounds like the bent geometry. And just to wrap it up with oxygen, 4 different things attached to it, 2 bonded atoms, 2 unshared pairs of electrons. All right, it looks linear based on how it's drawn, but remember, that can be deceptive. We've got unshared pairs of electrons. That's going to change the geometry, and we should observe bent geometry around the oxygen atom. So that's really what I expect you to be able to do with orbital hybridization. I know we talked a lot about the theory to begin with. If you choose to take chemistry courses in the future, I'm sure it's a topic that you'll visit again. But as long as you feel comfortable walking through the practice problems like we did with 2 and 3, you've got what you needed from this lesson. Good job today, chemists. Thanks for tuning in, and I hope you found this helpful.